probably she can speak, not a problem. And Chaitanya, are you there? Is that Chaitanya? Okay, uh, no problem. Well, I think it seems like Yashodhar will join in a short time, and then we'll do that. We are doing a course in topology. Before I give you introduction, we'll start a course in topology. I've already mentioned we'll follow two books. One of them is G.F. Simmons, Topology and Modern Analysis by G.F. Simmons. Okay. And
good morning, sir. And
good morning, Shraddhanjali.
Shraddhanjali. Yeah.
Okay. And we'll follow a course in topology, first course by James Munkus. Okay. I was looking at things, I just writing my own notes there, not much, but then I realized that topology by Morgan Simmons and modern analysis by Simmons is kind of very nice, and we can do follow mostly the same book. Okay. You're welcome to go through that book. Things may not be exactly what it is there in that. Is it okay. So to start with, what is topology? We need to talk about that first. Topology is more about studying the properties of some spaces under certain continuous deformations. If you take a space and continuously deform it and becomes another space, whether some of the properties that I had in the original space are retained after this continuous deformation or not. What is continuous deformation? If you take an object, I can move it back and forth, or maybe I can imagine you have kind of a rubber kind of thing, or maybe dough. You can maybe squish it, you can pull it, you can twist it, but you should not tear it apart. Those are what I want to consider as continuous deformation. So you can take that and just maybe twist it like that, or maybe fold it. You can crush it, and you can stretch it. Like you look at a rubber sheet, you stretch the rubber sheet this way, that way, or you can fold the rubber sheet. You can roll it. You are welcome to do all these things are continuous deformations. Okay, and if you take a rubber sheet, and suppose I have a rubber sheet here and I have a circle drawn into them. As long as you don't tear it, that circle probably will get elongated or maybe squished, but that circle will remain something of that nature. So we want to understand what properties of the space will be retained even under continuous deformations. The study of that is what really topology is. Okay. Just say, for example, I have the entire plane. In the entire plane, I drew a circle here. Okay. There's a circle drawn here like that. And that circle will divide the plane into an inside and an outside. Okay, anyway, this is the rubber sheet. Suppose I hold this rubber sheet and stretch it this way. This circle becomes elongated this way. Or maybe I stretch it this way, the circle becomes elongated this way. Maybe I stretch it, squish it a little bit here, squish it a little bit, the circle may become something like that. Okay, but whatever you do, the circle will not become something like this. Okay, it will not knot itself onto itself. It will not do that in that particular space, right? I can have, so that's what it is. In all cases, the entire plane of this rubber sheet will have an inside of this region and an outside of this region. Okay, this is what you understand from that. Okay. Of course, if you really look at it, this is in two-dimensional space. So this is x-axis, this is y-axis, and this is the z-axis, and this circle is set of all points x comma y comma 0, where x squared plus y squared is equal to 1. So there's a unit circle. Okay. Okay, that's fine. Let me explain something. Basically, continuous deformations have to be understood. I can give you a couple of continuous deformations. Let's say, for example, I have a cylinder like that. Okay, I can deform the cylinder like this. I can keep this piece here and make it a little longer. Can I do that? I can deform it. I can even slowly push it down and it becomes a annular region. So this will be deformed to this, will be deformed to this, and this is the annular region enclosed between two different circles. Okay, so this kind of a deformation is what I want to do. I want to look at actually one of the statements a lot of people see is that in topology, donut and coffee cup are one and the same. A donut, for example, a donut, I'm sure everybody knows a donut, uh, eh, right? It's a torus, really. You have a donut like that. Okay, I want to sort of deform this donut. There is a hole here, right? You know what a donut is, right? It's like a ring-shaped thing. Okay, and I deform it like this. I keep this part here and maybe make it a little long. Okay, you see, this is the same thing. The upper circle has gone and become a little longer. And let me deform it even further. I want to deform it like this. You see what I did? Okay, this portion, I bent it like this. So essentially, you have one circle here. Outer circle is just, this is the outer circle. I made the outer circle to look like this. Is that right? And there's the inner circle is right there. And now it suddenly looks like a coffee cup, right? So I can deform this torus into a coffee cup. So the topological transformations are basically, as I said, continuous deformations. I can continuously deform a torus into a coffee cup, or a coffee cup back into a torus. So in a sense, the properties that the torus has will be retained by the coffee cup. Indeed, I want to know what properties of the coffee cup will be retained by the torus and vice versa. That is exactly what topology is all about, to study what properties are retained. Okay, if I have a topological space, we'll talk about what it is, and the topological space is there, and in between there is deformation. What properties will go here and what properties will be coming from there and back and forth. Okay, if you can have both ways, a certain topological function transformation, okay, uh, can I say that this is exactly the same as that? Or what properties of this are retained by this? Historically, we'll go to the new page. Yeah, there is one more thing. Euler actually found out that if you really look at, you can see it easily. If you look at a tetrahedron, okay, like that, there's a tetrahedron, okay. It has 1, 2, 3, 4 vertices. How many edges are there? 1, 2, 3, 4, 5, 6 edges are there. How many faces are there for a tetrahedron? I think on all three sides, 3 faces, the one at the bottom, 4 faces are there. Okay, you have 4 vertices, 6 edges, and 4 faces, and you look at V minus E plus F, you calculate that, which is actually 2. As a matter of fact, if we take a sphere, and on that you take 4 points, and you can make these are all great circles you can draw around, and you have prepared a tetrahedron, right? And the tetrahedron has this property. Indeed, if on the sphere, if you triangulate it in any way, triangulate means you fill it with lots of triangles, okay? You fill it with lots of triangles. and there is this triangle. The whole surface of the sphere is cut into a lot of triangles. We will talk about this later on. For the present, I put a lot of triangles so that only any two triangles will share either a edge or a vertex only. Okay, you don't want a triangle to go like that. Okay, you don't want a triangle to go like that. So anyway, if you look at all bunch of triangles that I can prepare in that, in this also, if you calculate number of vertices minus edges minus faces is equal to 2. Whereas if you do the same thing on a torus, okay, if you do that, that number of vertices minus edges plus faces will be it will be 0. If you do it on a coffee cup, okay, you get the same thing. You get the number 0. As a matter of fact, this is what is called Euler characteristic. Euler characteristic will be retained by the topological transformations. We want to see that down the line. So there are certain invariants which will not change even if you continuously deform the surface into something else. Okay. I want to see something more in topology. If you really look at, for example, here is a plane, and there is a little patch which is removed off the plane. There is a little another patch which is removed on the plane. So there is a hole to the plane. There is a hole to the plane. Okay. And actually, if I don't have any holes, this is the plane. Suppose I have a circle here or some closed curve, doesn't matter. You can actually deform this closed curve into that. All you do is keep on moving and adjust it, and continuously you can move it until this curve coincides with that curve. Is that right? Whereas if I take a curve around this hole and you take another curve around this hole, there is nothing I can do to take it and make it coincide with that, because the hole will stop you from coming out. You understand that? There's a hole. So that's not part of the space that you have. The space is the entire real line minus these two holes, hole 1 and hole 2. So I cannot move this circle out of the hole. It's stuck. Hole is in the middle and it's stuck around there. So there is no way it goes there. You cannot move it from there to here. Actually in the space R cross R. But if I have another axis here, if I bring in a maybe x-axis, y-axis, and z-axis, then you can take this and go into the space, go like that and put it here. Oh, I see. I can continuously deform it, keep on changing it until it becomes that. Once you go for extra dimension, you see suddenly that I can deform it into that. So this space as it is, R cross R, with these holes removed, doesn't have that feature. So the dimension is also going to matter whether I can deform one into the another or not. For example, I'll tell you this. Suppose I have taken a knot, something like a knot like that. Okay. Okay. Something like this. Okay. Let's see. Hang on a second. Okay. Right. Okay. I take a knot like that. You see that? I actually brought a little sheet. I forgot to bring it here. So you have taken a rope and you went around and you knotted it. Okay. Right? You knotted it. Now, do you think you can release it? You cannot release it. So you cannot deform into just a simple circle. You cannot deform it into a simple circle because you put a knot inside there. I hope everybody understands that. That is in R3. But if you allow one more extra dimension in R4, we will show to you that I can actually untie this knot and just make it almost every knot you create in R3. If you have one more extra dimension, it just releases and it becomes this. Okay? I mean, these two are topologically equivalent if you are in the space R4, but in R3, they are not topologically equivalent. Okay? I'll tell you some more things. Let's say I have a circle here, and I have a point inside, I have a point outside. Can you go from this point to that point in a continuous way in the plane? In the plane, let's say this is the plane. X-axis, Y-axis, and here is one point. Maybe there is a Z-axis also. But I'm operating in the plane that is 0, 0, 0. And there is another point, 2, 0. Maybe put this point here, who cares? Put it here. Okay, 2, 2, 0. That point is outside the circle, right? In two-dimensional geometry, as it is, there is no way I can draw a curve from this point to that point without intersecting this thing. There is no way you can go. If you want to go like that, you have to cut this, is it not? But in 3 dimensions, you can go out that way to that place. Everybody accept that? Okay. Now suppose I have a sphere. I have a sphere. And I have a point inside the sphere in the 3-dimensional space. I have a sphere in the 3D. I can tell you this deformation is not a very big thing. The deformation is like, you can say, let's make up something like, maybe I want to go from here to 2, 2, right? So I say 1 minus, okay, yeah, I should go from here to here. Yeah, 2t, and t, 1 minus t. If you look at this transformation, f of t, initially when t equal to 0, it is 0, 0, 0. Finally, when t equal to 1, it is 2, 2, 2, 2, 0. Yeah, I've gone from 0, 0, 0 to 2, 2, 0. And you know what? No, this circle is set of all x, y, 0, where x squared plus y squared equal to 1. Okay? And this will not intersect this circle at all. You can go, that is what I'm doing, is I'm climbing up and going to that place. Is that okay, sir? Everybody okay? That's obvious, right? So I'm able to have a continuous function written down over there, which will take you from this point to that path through a path, right? Whereas, let's look at a sphere like this, a full sphere in 3-dimensional space, and there's a point inside, there's a point outside. Now, can you write a path from point inside to the point outside without intersecting the sphere? Yes or no? Can you do it? You can't do it in 3 dimensions. But in 4 dimensions, it's just the same way. You take a full sphere, there's a point inside, there's a point outside. Okay. In 4-dimensional space, I will be able to write a path which will go without intersecting the boundary of the circle, the sphere, and it goes out. Indeed, for a sphere of the 3 dimensions in R-dimensional space, there's no inside, there's no outside. There is only one side. For a circle, in the 2-dimensional space, there is inside, there is outside. But if you look at the circle in the 3-dimensional space, there is no inside and outside. X-axis, Y-axis, Z-axis. If I take just a circle inside this space, inside the space I take a circle. Is there an inside and outside? There is no inside, there is no outside. You can go through the circle and come out without intersecting the boundary. So for a circle in two-dimensional space, and when that is in three-dimensional space, there is no inside, there is no outside. Similarly, for a sphere in three-dimensional space, as seen as a subset of R3, there is no inside and there is no outside. I hope you recognize that. I want to see all these things, okay, through topology. I'm not promising that I can do everything that I am trying to tell you, but maybe towards the end, I'll take a very short course into algebraic topology, if I can. Then I can tell you all that. The basic general topology will give you general setups, but maybe I cannot. I can solve some of those problems, not a big deal, but maybe I cannot do every one of them. As I just said, a knot. You know what a knot is like? You go there, tight underneath that. If you go all around and go from underneath that, there is no way in real space you can pull it apart and make it a simple path. You cannot do that. But in R3, R4, you can really do that. In just the same way, the sphere has an inside and outside sphere, two-dimensional sphere. Inside R3 has an inside and outside. But this two-dimensional sphere, as sits in R4, has no inside, no outside. We need to understand these things. There are a lot of nice things indeed. As old as 1750s and so on, I think Euler was the first one to really realize there are certain things can be done. There was a very famous Königsberg. Königsberg is a little town, and there is a kind of a river, and there are two islands inside the river, and apparently the municipality has done that. It has put some bridges just for entertainment. There were a lot of bridges, okay, like this, and there is a bridge in connecting them too. And the object is to start anywhere and cover all the bridges without covering any bridge more than once. You start anywhere, you go over that, you go over that, you go over that. Oh, I think I'm going to be stuck. I can come down and come back up. I have to go this way, then I cannot traverse on this. If I go this way, I cannot traverse on this. So the question is, can you find a possible route to start anywhere of your choice and come back finally to that place by covering all the bridges, each bridge only once? It is very easy to show that it's not going to work out. And Euler has shown that. And basically, I think the degrees, this is something we teach you in graph theory. You easily understand that this vertex of the graph has degree 3 and this vertex has 5. And every vertex has an odd degree. So there's no way you can have such a path. So this is the starting of, okay, somehow converting into another form in which I want to solve the problem. These are the ideas. Euler was one of the first people to think about some ideas about topology. And down the line, I think perhaps Henri Poincaré was a famous French mathematician, was very instrumental in developing the subject very thoroughly. Even around that time, there is Felix Klein and Brouwer and Kuratowski was also very much instrumental in developing a lot of topology. A Polish scientist, I think, Alexander Kuratowski was also instrumental in doing that. So topology is more like a rubber sheet geometry. If you have a rubber sheet, which can be stretched this way, stretched that way, or rolled over, folded, you can do all sorts of things. You don't want to tear it up. Then if you draw in that rubber sheet a closed, simple closed curve, of a lot of rolling and all that, what does that simple closed curve become? It will still say a simple closed curve. Okay? So topology, some people say, is more like a rubber sheet geometry. So if you deform, continuous deformation, no tearing, okay, you can roll, you can fold, you can twist, you can stretch, you can squish. These are all things that you can do. Rigid transformations are anyway acceptable. And when you do all those transformations, and the point is, what is that you see that remains unchanged? What curves remain unchanged in the process? What properties of the curves, what properties of the surfaces remain unchanged in this process. Study of that is what topology is all about. I hope I have made some introduction really to and genuinely verify some of the things that I said. I will have to teach a lot more than just topology. Okay, we're not going to do that right away, but down the line, if I have an opportunity, we'll do it. Okay. Indeed, I think my physics teacher also said that apparently an electron, when you rotate it 360 degrees, it will not be the same. You have to rotate 720 degrees for it to be the same. We have a nuclear physicist in our group, he knows that. So what does it mean? If I rotate 360 degrees, I think I'll come back to the same person. But electron doesn't seem to do that. If you rotate 360 degrees, it will probably from spin up, it go down or something. And then you have to rotate another 360 degrees for it to come back to spin up. Okay. You can see that in the three-dimensional space, there should be some extra dimensions in which that is very obvious. Actually, that kind of gives you a little feel about what it is. Indeed, we see lots of examples, this is one example I should have mentioned there too. If I look at a torus, there is a donut. If you take a circle like this, I can contract it to a point. Okay, this circle can be somehow deformed into another circle there. But if I take a circle all around it, no matter what I do, this circle cannot be deformed into that. I can also take a circle all around the top. No matter what you do, this circle cannot be deformed into that. So what can be deformed and what can't be deformed, all those things will dictate a great deal. Indeed, algebraic topology is one way of attaching algebraic structures with such topological spaces, and your understanding of algebra will somehow translate to some ideas in topology. That's what algebraic topology is all. It's very nice. Just as we do in coordinate geometry. What is coordinate geometry? Coordinate geometry is geometry, you somehow associate algebra to it and convert it to algebra, and geometry synthesis is what is going to give you coordinate geometry. Every little geometric object you see in the three-dimensional space, you associate with that an algebraic equation and manipulate the algebraic equation through mechanical laws of algebra and convert it back into you interpret back into geometry. That is how the problems in geometry are done. You do the same thing here. With each topological structure, we associate a hierarchy of groups, algebraic structures, and the understanding of those algebraic structures will tell me a great deal about the topological surfaces. Okay, I think I don't want to say anything more than that. All right? Anybody have any questions? Okay, we are going to start topology. Formal definitions of topology and so on. Okay. Let's start with the formal definition. Let X be a non-empty set. Okay. A collection T of subsets of X is called a topology on X. A topology on X if the following conditions satisfied. First condition is if the null set and the entire space both are in T. T is a collection of subsets of X. X is an unempty set, and looking at lots and lots of subsets of X, and they're all put in this family T. Script T consists of a collection. It consists of a lot of subsets of X. And what are the properties it satisfies if empty set and X are actually in T? 2. Okay. For any subcollection, perhaps I take G alpha in delta. So this is some indexing set. So I have taken maybe the indexing set maybe 1, 2, 3, then it is G1, G2, G3. But delta can be very rich. It doesn't have to be finite. It doesn't have, can be infinite or uncountable, uncountably infinite. It can be anything. I have whole class of sets G alpha. For any subcollection G alpha, alpha in delta of T, the union of all of them, union G alpha, alpha in delta is also in T. So if I take bunch of objects in T, their union also must be in T. And 3, for any fine subcollection, okay, maybe G1, G2, etc., Gn of T, their intersection Gk, k equal to 1 to n is also in T. So that means if you take finitely many, their intersection should be in T, but arbitrary many and their union must be T. I'm not asking arbitrary many things intersected into be T. I don't want to take that as a condition. Only P, this is what I say. P is closed under finite intersection. Is closed under finite intersection means if you take finitely many of the G's in T, their intersection is in T. It is also closed under arbitrary unions. If you take arbitrary collection of arbitrary collection of sets G alpha in T, their union is in T. Okay. So then I say T is a topology annex. Okay. If T is a topology annex, we say X comma T is a topological space. A topological space is an ordered pair. An underlying ambient set X and some collection of subsets of X would satisfy this property. That is a topological space. However, actually what we do is we often say X is the topological space, and one should understand that appropriate T is already there. So oftentimes I say let X be a topological space. That means T is already there and it is understood. Sometimes I say X comma T is a topological space. Many a times we'll just say X is a topological space, and you have to understand what I mean by that. Okay. Note, if you really look at the condition 3, which is T is closed under a finite intersection, you can see mathematical induction can be applied to show that 3 is equivalent to 3 dash, which is 3 dash, which is for G1, G2 in T, G1 intersection G2 is in T. That's enough. If you show intersection of any two things in T is again in T, then you must have proved this by mathematical induction, right? For two things you did, for one more, So you can use principle of mathematical induction to prove that, if two things given in T, their intersection is in T, then any finitely many given in T, their intersection is also in T. Not only that, okay, these two conditions, as I mentioned, 2 and 3, are respectively said to be the properties of the T being closed under arbitrary unions and mean, respectively, that T is closed under arbitrary unions and finite intersections. Okay. Actually, in the Simmons book, he has something else. He says Arbitrary union means in case this collection is an empty collection. What is the meaning of a union of an empty collection? You have to define what union is. Union of an empty collection will be empty set, and the union of an empty intersection will be big space X. So if you really define intersection of GK, I said K equal to 1 to n, K belong to some underlying set. Okay. In case delta is empty, actually this is set of all X such that X is in GK for all K. Okay. I have taken all these GKs are subsets of X. So in case delta is empty, this intersection GK, K in delta will be the whole space. You can logically see what happens. If you take, you have to say it is X. If it is not X, at least one element must be missing. What do you mean by one element of X is missing in the intersection G? Is missing in the intersection G, K in delta. It is missing. It means it is in is not in one of them. Okay, and it is in one of them. Maybe it is not in one of them. That is a problem. Okay, because there is nothing in delta. You say that it is not in this. Okay, so I think because of the logical thing, you will see that it has to be X. You can read Simmons' book and understand that small point there. Okay, actually, in the intersection, it is not there, maybe it's in something and it's not in something. If it is not in one of them, then you can say that. But there is none of them. I can say it is not in one of them or it is in one of them. Okay. So Simmons probably doesn't even want to write these two extra conditions that empty set and the whole space belong to T. But I would like to write it all the time. Okay. Uh, so if you say empty intersection is the whole space and empty union is empty set, then these two conditions actually will take care of this first condition. But I don't want to follow that notation. Yeah. Okay. So always when I take a collection, I take a genuine collection, and their arbitrary union must be T, and any finite subcollection of T is taken. Its intersection is T. That's what our definition of a topology is. And if T is a topology on X, I see Xt is a topological space. But oftentimes I'll just say X is a topological space and not pay attention to that term T there. Let's take some examples. Okay. Example 1. Take any non-empty set X. Let X be a non-empty set. And in T, let us keep only the null set in the whole space. This. Okay, both of them are in T, and their union is X. If I take both the sets to be empty set union, empty set is empty set union X is X, empty set intersection is empty set, X intersection X is X. I think T satisfies all three conditions of the topology. Therefore, this is a topology. Is a topology on X. It's called indiscrete topology of X. Called indiscrete topology on X. Okay, so very obvious example. I will take another example. Again, let X be a non-empty set. And in P, you take the entire all subsets of X. Every subset is in T. So if you take every subset is in T, empty set is in T, and the whole space is in T. They are subsets of X. And if you take any bunch of subsets in X, and their union is also a subset of X. So action 2 is satisfied. And finally, when you take of them, their intersection is a subset of X. So action 3 is satisfied. So naturally, it's an easy thing to see is a topology. This topology has every subset of X is a member of T on X, called discrete topology. Everybody okay with that? Not much to verify. So you see, naturally, on a single set, I can have more than one topology. Many topologies can be introduced. That's why when you say topological space, underlying set and the family T also should come. But if things are understood, you know what is the underlying set, we should know what is the topology on X understood, then you just say X is topological space. Don't even bother writing T all the time. Okay. I will introduce another thing. Let X be a non-empty set. Preferably, I would like to take an infinite set anyway, preferably infinite set. I don't have to say that. Even if finite set is okay. But infinite set gives you a nicer thing. We're going to define T to consist of all those G such that either G is empty or complement of G is finite. Okay. Actually, X minus empty set is meaningless. That's why I said either G is empty. If it's not empty, then I want X minus G to be a finite. That's when I say that G will be in T. I want to show you that T is a topology on X. For example, empty set is in T. Already said that. Okay. So if you look at the whole space minus X is empty set. So that's fine. Therefore, X itself, hence, X is in T. Are you understanding that? X minus X is fine. So X is like G, and that is in T. So both empty set and the whole space is in T. If I take an arbitrary collection, let's say G alpha belong to delta, be a subcollection of T. I want to say that their union is in T. Well, actually, if I look at a lot of things, maybe they're all empty. If they're all empty, their union is also empty, and then that is in T. If G alpha is empty for all alpha in delta, then union G alpha in delta is empty too, and that is in T. So if one of them is non-empty, suppose there is an alpha naught in delta, so that G alpha naught is non-empty. Oh, but if that is a non-empty set, I think it is in T only when the complement is finite. Therefore, X minus G alpha naught is finite. Okay. Then I'm trying to look at X minus union G alpha in delta. Oh, the entire union is subtracted and only G alpha naught is subtracted. Don't you think this is a subset of G my X minus G alpha naught? Okay. I'm subtracting the entire union. Here I'm only subtracting G alpha naught. So this is contained in that. But that is finite. And therefore this has to be finite too. Okay. It's a subset of a finite set. Hence, X minus union G alpha naught, G alpha in delta is finite, which actually means that is union G alpha in delta is in T. So if I take a subcollection of T, their union also is in T. Either all are empty or one of them is non-empty. In both cases, if all are empty, then also union G alpha is in T. If one of them is non-empty, then also union G alpha is in T. So union G alpha is in T. That means T is closed under arbitrary unions. Okay. I want to show it's closed under finite intersections. So let G1, G2, let's just do it for two things. For anything else, so we can do anyway. G1, G2, etc. Gn be in T. Okay. If one of them is empty, if there is an alpha, there is a K. If there is a K, 1 less than equal to K less than equal to N, and such that GK is, maybe I say GK naught, okay? GK naught is empty. Then the entire intersection GK, K equal to 1 to N, is empty too. One of the sets is empty, so the whole intersection is empty. Hence, intersection GK, K equal to 1 to N will be in T. Empty set is in T anyway. Oh, but if every one of them is non-empty, what happens? In case if GK is non-empty for every 1 less than equal to K less than equal to N, for a non-empty set to be in T, for a non-empty set to be T, the requirement is X minus G is finite. So if they're all, non-empty, okay. So if they're all non-empty, then because they are on T, so X minus GK is finite for all 1 less than equal to K less than equal to. So you have a bunch of finite sets, and if they're all finite, their union is also finite. Therefore, union GK, K equal to 1 to N, union of finitely many finite sets. Finitely many finite sets, their union is finite too. Sorry, I take it back. Therefore, union X minus GK, K equal to 1 to N, which is a finite set, their finite union is finite too. But then you notice that this is same as intersection GK, K equal to 1 to N, X minus that. So that is finite. That means this intersection is in T. Hence, intersection GK, K equal to 1 to N is in T. So either way, I proved that T is closed under finite intersections and the arbitrary unions, and the empty set of X are in T. Therefore, T is the topology. Okay. This topology has a name. This is called a cofinite topology. I put a name to it. Okay, this is called a cofinite topology. Okay. Actually, see, in case X itself is a finite set, then X minus G is always finite. So every subset will have X minus G finite. So in that case, if X itself is finite, the cofinite topology becomes a discrete topology. Is that clear, sir? So note, in case X is finite, the cofinite topology on X is the discrete topology. Okay? Good. Just the way you have introduced cofinite top. Any questions, sir? Not much anyway. Yeah. You have the next is co-countable topology. In this case, once again, take any abstract set X. Let X be a non-empty set. I think preferably uncountable set will be better. Okay. Otherwise, you will degenerate to discrete topology again. Let X be a non-empty set, preferably uncountable set, and T consists of all subsets G of X, where either G is empty, okay, or X minus G is countable. In exactly the same way I proved, you can prove that this is a topology on X. Okay, in just the same way as we did above, we can prove that T is a topology in X and this is the co-countable topology. Okay, right? So T is a topology in X. I leave it as an exercise. You can, it's left as a exercise. And indeed, if X is countable, this is degenerates to discrete topology. If X is countable, even countably infinite countable, T is the discrete topology. Okay, so I see that in a topological space, on a non-empty set, I can have plenty of topologies. Okay, we're not going to answer how many topologies are there and things like that, but I want you to recognize that many topologies are in given abstract set. Okay, now a little definition. If you have a topological space, Xt, the members of T are what are called open sets of the topology. Okay, here is the definition. Let Xp be a topological space. After a while, I don't want to write Xt be a topological space. I say let X be a topological space. Okay, slowly I will abandon writing T unless it becomes imperative. If you have two different topologies are discussed at the same time, then I got to be very careful. Should I use the T1 or T2, things like that? Otherwise, I just say X is a topological space for a little while. Let X be T be a topological space. Okay, any element in T is called a T open set. I will just usually say just an open set or just an open set if T is understood. Or just, okay. Any element in T is called an open set. Is called an open set. We say T open set also in case X has two topologies T1 and T2. Is it an open set from T1 or is it an open set from T2? That is also important, right? So in that case, I say it is a T1 open set and that is T2 open set. One open set in this may not be open set in that. You know very well. Very soon you will understand that. Okay. So I say, oftentimes I say, very loosely I say, let G be an open set in X. I'll just say that. That means X has an underlying topology. It's endowed with some topology T, and G is an element of T. That's what it is. Okay. Many a time we say G is an open set in a topological space X. That is how loosely we write. What we mean is that on X there is a T, and this G belongs to the T. And in case of two topologies, then I have to be very particular with respect to what topology this set is open. Let's take some examples for you to actually feel. For example, in the discrete topology or in the indiscrete topology. Indiscrete topology is a topology with only empty set and X. So only open set are empty set and X. Everything else is not open. By the way, when you say not open, don't say it's closed. I have not defined closed. Not open, that's all. Open or not open. Okay, so here empty set and X are the only open set. You understand that? Sir, I will give you a lot of examples of topology down the line. As yet, I have not have enough techniques to create too many topologies without enough work. So we'll slowly give you more and more examples. Okay. Indeed, the usual examples are most important, and we'll give those examples slowly. Empty set and X are the only open sets in it. Anything else is not open. In the discrete topology, what is discrete topology? They are X together with the power set of X. That is the topology. Oh, every subset is a open set. Okay, every subset of X is an open set. You understand that? Let's take another example, maybe the cofinite topology. What I will do is I'll take X to be the set of all integers, Z. Okay, I'll take X to be the Z endowed with cofinite topology. Okay. Now, if you look at set of all natural numbers, any set of all natural numbers, it is a subset of Z. It's not empty. Its complement is not finite either. So what is N? It's not open. Okay, N is not open. Why? Because neither N is empty nor complement of N. What is that item? Z, right? Complement of N, X minus N is finite. And that is infinite. I mean, all the negative integers and 0 are there in this. This is an infinite set. So I think N is not an open set. But you can create a lot of open sets very easily. You can create, for example, for every integer N, okay, the complement of that integer, N complement. N complement contains everything other than N. And clearly X minus Gn is only singleton N, right? Then X minus Gn has only element N, which is finite. And therefore, Gn is an open set. Gn is in the topology. Therefore, Gn is in T. That means for every N complement indeed, for every finite set, complement of every finite set is an open set. Indeed, open sets are all those things. Okay, so indeed, other than empty set and the whole space. Okay, other than a null set and a whole space, I have physically a whole space is anyway there. All complements, all open sets are complements of finite sets only. Of finite sets. Okay, so that's what your cofinite topology, open sets and cofinite topologies. Okay, I think you understand what open sets are, right? And if you read,
I think you haven't completed the definition and you started examples. We go to the definition of open set. Next page.
Oh, next page. Okay. Yeah.
Next page.
Okay. Okay.
The definition was not completed.
Any element of T is called an open set.
Okay. Any element of T is just a subset of X, basically.
Yes, but not every subset of X is an element of T, right? Those members of the topology are called open sets. Okay. Any element of T is called an open set, or sometimes I say it's G open set. So, as such, for example, in the indiscrete topology, the only elements of the topology are empty and X, and these are the only open sets. Okay. Later on, I said that as many times I don't write T at all. I'll just say G is an open set in the topological space X. I will say what? G is an open set in the topological space X. That's what we say. When will that be an open set in X? If X is in the underlying topology. Okay. If maybe I should make this many a time. We say G is an open set in topological space X if G is in the underlying topology of an X.
Okay.
Topology on X. Okay, actually, I didn't want to write all that. I just say open set in X. But what the open set in X means what? It is in the topology T. That's what open set for us are. members of T are called open sets. Okay, that's the first definition there. I hope now you can clearly see in cofinite topology, the N is not open. Okay, because it's not empty set and its complement is not finite either. But if you take complement of any finite set, its complement is finite and therefore it is open. Okay, and going back, okay, previous. What we are saying from the very definition of topology is topology on X consists of open sets, which are this second condition says arbitrary union of open sets is an open set. This third condition says that finite intersections of open sets is open set. So the kind of actions 2 and 3 tell you that arbitrary union of open sets is open sets and finite intersections of open sets is an open set. Let's go to that. Okay. Let's go to that. So thus action 1 says empty set and whole space are open in any topological space. Okay, and in any, so actions 2 and 3 respectively mean that arbitrary unions and finite intersections of open sets are open. Okay. Okay. Well, actually, when you say open set, you want to talk about closed set. It is the definition of a closed set. Okay. Let X be a topological space. See, we'll be careless. We don't write the topology. We just say let X be a topological space. A subset A of X is said to be closed if its complement X minus A is open. Okay. I'll say a set is closed if its complement is open. Okay. So as such, immediately you see that empty set's complement is whole space that is open, therefore empty set is closed. X complement is empty set and that is open, therefore X is closed. Empty set and X are closed in any so in general, maybe I'll write these things. Okay, it is easy to see. One, empty set and X are closed because their complements are empty and their complements are X and empty. They are open and therefore they are closed. And if you take an arbitrary union, arbitrary intersection of closed sets, so arbitrary intersection of closed sets is closed. Is closed. You can see that if I take a bunch of closed sets, each is closed means X minus A alpha is open. Okay, and therefore their arbitrary union, which is X minus A alpha's arbitrary union, is open too. But this is actually nothing but X minus intersection A alpha in delta. And so this is open, that means this is closed. That's what I'm saying. arbitrary intersection of closed sets is closed, and the finite intersection of closed sets. Sorry, yeah, that's why finite intersection. First, finite union. Take it back. Finite union of closed sets is closed. If you want just a little explanation for each one of them, there are the explanations here. Okay. So if A alpha, alpha and delta are all closed, then x minus A alpha are all open. Open sets means they are in the topology. Okay. If they are in the topology, then their union is also in the topology. Okay. Hence, x minus intersection the alpha, which is actually union alpha in delta, x minus A alpha. I don't need a bracket there, but anyway. X minus A alpha is an open set, and then arbitrary union, that is actually x minus intersection. This arbitrary union is in T, is open. And therefore, this has to be closed. Therefore, intersection the alpha and delta is closed. That proves this second statement, proving second statement. If you want to prove the third statement the same way, if you see, if A1, A2, etc., AN are closed, then for each one of them, x minus AK is open for 1 less than equal to k less than equal to n. And then you're talking about union of these things. What is union x minus AK? Not union. I wanted okay. So if finitely many are open, their intersection is open. So intersection x minus AK. Can you see this in your intersection? Can you see that? Is it visible, sir?
Yes, sir.
Intersection x minus AK. Finite intersection of closed sets k equal to 1 to n. Finite intersection of open sets is open. So this is open. However, this is actually x minus union AK k equal to 1 to n. Once you say this is open, this little piece here is closed. Hence, union AK k equal to 1 to n is closed. So as some of you have reverse thing, right? So arbitrary intersection of closed sets is closed, and finite unions of closed sets is closed. Okay. So anyhow, okay, I think I should virtually stop almost 11:30. Okay. So we have done very little. We talked about open sets. Open sets are nothing but the members of the topology that is on X, and a set is closed if its complement is in the topology T, if its complement is an open set. I have not given you enough examples yet. Okay. In the discrete topology, every subset is open, right? And therefore, every subset is closed also. If you take any subset, its complement is a subset that is open, so that subset is a closed set. So in the discrete topologies, all are closed sets, all are open sets. Okay. So I'll stop here. We will meet again on Wednesday. Okay. I will send you the notes also slowly. But mostly, as I said, I would follow G.F. Simmons' topology and model analysis. You can read. Even then, I'll send my notes. Any questions, sir?
Nope, I think that's good.
Okay. Okay. Uh, actually, go ahead.
There is a question from, I think, Chaitanya. He
Mhm.
he wanted to understand what the three actions are. Is unable to ask the question on his mic is not working.
Okay. Okay, we'll go back. Definitely. Uh, okay, there you go. Yeah, these are the three actions of the topology. A collection of subsets T of X is called a topology NX, provided it has null set and the entire space. Maybe I should give you a little a light-hearted example. I can say in X, I use, oh my goodness, hang on a second. My pen is to be, just a moment, will be there soon.
I guess the question is, why are they not called axioms? It's basically the definition of topology.
They are the actions of topology. They are, why did I say actions? They're just, they are the three conditions that require the family T to satisfy in order that it's a topology. So that's what it is. Um, yeah. Why did you call actions? You just say conditions. Yes. If that is the case, I will agree with you. So for example, if you take in X the numbers 1, 2, 3, 4, okay, that's all. I can put in T, maybe I can put empty set and the whole space. I can put singleton 1 and singleton 2 and set containing 1, 2. It satisfies all these conditions. Null space is there, whole space is there. This is there and this is there, their union is there, their union is there. So this becomes a topology on X. Okay, so topology is a collection of subsets of X which are required to satisfy these three conditions. Apart from null set and the whole space is that if you take any subcollection of T, their union ought to be in T, and finite intersection has to be in T. Actually, why this condition? People can ask other conditions. Actually, you will see that, if I really wanted the topology also to be closed under infinite subcollections, a lot of very beautiful examples which we use in analysis will all go out. They don't work. I think this is the optimal things will work. Maybe later on, sometime I say why this definition is so very much needed, so very much accepted, not something else as a definition. Okay. This comes from the idea of the concept of a neighborhood. You talk about in metric spaces. The neighborhoods actually satisfy this condition. Okay, so only those conditions will take into it. Does that answer your question, Chaitanya? These conditions is what we are looking for. If they satisfy, call the topology. For the present, it's just definitions, right? Doesn't matter what we define. But down the line, you see the value of this definition. It actually does a lot of good work for us. Somebody has written a small something here. Okay, fine. I can read it there. So that's it. That's what we really mean. A topological space is a set together with a topology. The topology should satisfy these conditions. And members of T are called open sets. In case X has two different topologies, right here I can have another topology. This is topology 1, and this is topology 2 that contains empty set, whole space, singleton 3, singleton 4, and the set containing 3, 4. Now you see that this is a T2 open set, but in T1 there's a closed set. In T1 this is open set, so its complement is 3, 4, and that is so. In this case, singleton 3, 4 is a closed set, whereas in this case, singleton set containing 3, 4 is a open set. Okay, so open sets are members of T. Okay, we'll take more examples maybe next time before we continue. Thank you all very much. We'll see you on Wednesday.
Thank you, sir.
Okay.
You please share if you have any comments. You can share it in our group. You can send some comments, some things for which you need a answer in the next class. You can just send it. You can share your questions. Definitely answer. Okay, this is a very easy subject. Maybe in the beginning, the abstraction might kind of throw us off. Abstraction might trouble us as to why anybody defines like this and so on. But down the line, you will see that's there is a beautiful definition. But more than anything, my introduction told you what I am really doing topology for. Actually, understanding continuous deformations and what properties of one ambient starting space, what properties of a space are retained through continuous deformations, what properties are lost. The whole story is all about that. And actually, and when algebra is attached with topology, you get such a great flexibility in deciding all these things by just some equations. Indeed, for example, knots are there, where the two knots can be homotopically. With each knot, we associate certain polynomials. And just one look at the polynomial says the polynomial of this knot and polynomial of this knot. You look at it and say, sorry, these two polynomials, these two knots are not the same. Okay, so the very difficult choice of knots are very, you can have a very bad knot and another bad knot, and can you convert that knot into this? That's a question. But if you associated the polynomials or looked at it, you can easily see whether the two knots are one and the same or not. So that way, when algebra comes into it and you study algebraic topology, I'm very poor at it. I know very little of it. I can understand and teach you in any of the courses. That's a different matter. But I'm not an expert in algebraic topology. But it is definitely uh, quite a useful tool in understanding analysis. Okay, that's about it, sir.